All right, everybody, can you hear me?
Yes.
I guess it was.
Yes.
Good. All right. I'll wait for a few more seconds, and then we'll begin. Yep. Okay. So this is lecture 3 of Intro to Deep Learning. Today we're going to start the discussion on how we can learn a network. So the topics we're going to cover are the problem of learning. We'll look at the perceptron rule for learning individual perceptrons and why it cannot be used to train multi-layer perceptrons. We have in the slides information about Adeline and Madeline. I won't be covering them because we won't have time, but I expect you guys to go over the slides because these things will turn up in your quiz, and we'll learn about empirical risk minimization. So here's a quick recap. Feel free to interrupt me at any time. If you don't understand anything, please ask, right? We've seen that neural networks are universal function approximators. What this means is that given any function, you can always construct a neural network to compute it exactly or approximately with arbitrary precision. So you can model any Boolean function, you can model any classification boundary, you can model any continuous valued function using a neural network, provided the network satisfies some minimal architecture constraints. We saw this in the last class. Networks that have fewer than the required number of parameters may not work. In fact, they can be very poor approximators. For instance, if you're trying to train a neural network, if you're trying to construct a neural network to compose the XOR function, if you're even one neuron shy of the minimal number of neurons, then the network is going to be wrong 50% of the time. So you need to satisfy minimal architecture constraints. We also saw that when we speak of AI tasks, these are generally input-output tasks. Something goes in, something comes out. And in each case, there's a neural network between the input and output. And these are functions. They take an input and compute an output. And because they are functions, they can be modeled by neural networks. So if you're going to be modeling these functions using neural networks, there are some natural questions. How do you represent the input? And how do you represent the output? Again, remember that neural networks are mathematical objects. So while you may be playing a game, the game state has to be represented in some kind of a mathematically interpretable manner. So also, the network may predict or give you a recommendation for the next move. The next move is something concrete, but again, it must be represented in a numeric manner. So how do you represent inputs? And how do you represent outputs? And how do we compose the network that performs the necessary function? So we're not going to be talking about representing inputs and outputs right now. We're going to focus on composing the network that performs the requisite function. Now, in what we've seen so far, our neural network is a networking of simple elements that we call the perceptrons. And the perceptron generally has a structure of this kind. In the general setting, it has a bunch of real valued inputs, and there's a bias term. The perceptron first computes an affine function of the inputs, which is the weighted sum of the inputs plus the bias. That gives us an affine value z. This affine value z gets put through an activation function And in much of what we saw in the last week, the activation function was a threshold activation. But then we also saw that you can have other kinds of activations for the network, for the perceptron. The parameters of the perceptron, which determine how it behaves, are these weights and this bias term. Now, the bias term is a separate term over here. But then there's a different way of viewing the bias term, which is to say that you can augment the input with an additional component whose value is 1. And then if we do so, then the weight of this additional input whose value is 1, Wn plus 1, effectively captures the bias. So in all of the representations, if I'm not explicitly showing a bias, then you must understand that I'm considering that the input has been augmented by this additional term, which has a value 1, and that its weight is going to be the bias. Questions, anybody? Is this clear? So again, I'm hoping. Yes, I mean, it's a bias. So the bias is so having a separate bias term is equivalent to having a separate input whose value is 1 and whose weight is the bias. There are different ways of setting it, but this is how we are going to set it up. Okay. Any other questions? All right, let me continue. So here's where we are, right? First, we need to define the structure of the network, and we're going to assume that this is a feed-forward network. That means there are no loops. Each neuron, anytime there's an input, each neuron will process the input and pass its outputs to downstream neurons, and that input is never going to cycle back and come back to the neuron. So each neuron sees the input exactly once. The network is a directed acyclic network. Part of the design of a network is the architecture. How many neurons, how many layers, how many neurons per layer, how these are connected, etc. For now, we're going to assume that the architecture of the network is known and that it is capable of representing the desired function. So now, when you have a network of this kind, then the entire network eventually operates on inputs X and produces some output Y. So you can think of the entire network as a parametric function where the parameters of the function are the weights and biases of the neurons that compose the network. So when we speak of learning the network, we are really speaking of determining the values of these parameters, namely the weights and biases of the individual neurons that compose the network. And our objective is to figure out how best to set these terms so that the network composes some desired function. So moving on. Any questions so far? Questions? No. Okay. Now, what we learned is that an MLP is a universal function approximator. It can represent anything. What this meant again was that a ML, given any function, say for example, this grid-shaped function over two-dimensional input, we can always construct a network that computes that function. But the question is, how do we construct this function? Now, we saw one example. One simple way is to just construct it by hand. For instance, if I wanted a network that could generate this decision boundary with a 1 inside the diamond and 0 outside, if I knew the shape of the boundary, I can just construct the network by hand. One perceptron for each of these edges, one to OR the lot, voila. I have a network that can compute this decision boundary. In the more generic case, you're not going to have such well-specified clear problems, and you cannot actually handcraft networks to compose compose the function that you're interested in. And so we have to derive the parameters of the network to best compose the function. So let's say you're given a function g of x, shown by this mesh here, which has a value for every possible input x. Then, if you want to construct a network fxw, the semicolon separates the input to the network from the parameters. So f of x semicolon w means that the input is x, the parameters are w. The w includes the weights and biases of all the perceptrons in the network. So given g of x, our problem is to figure out how best to set this weight w so that this network computes g of x as close to exactly as norm, right? So Leonard, we don't know the bias. If I, right, that's something to be estimated. It's like one of the weights. So how do we learn a network of this kind? How do we learn a network to compute g of x exactly? Here's how you can do it. Now, g of x is some function shown here by this dotted blue line. For any setting of the network parameters w, this network is going to compute some function shown here by this dotted red line. And the actual function that the network computes is going to depend on the parameter w. Now, if the network doesn't exactly compute your desired function g of x, there's going to be a gap between the function that the network computes and the function that you want. And that gap is shown by this shaded region. And now, in order to train the network, what we want to do is to determine the values w such that the area of the shaded region is minimized. You want it to go to 0. So what is the area of the shaded region? It's easy. Now I can define some error function which measures the gap between the target function and the function computed by the network at any x. And the shaded area is the integral of this error over the entire input space, as shown by this equation. And we want to estimate the w that minimizes this total error w. This clear to everybody? Okay, so this is easy enough, right? But then, in order to compute this error, we need to know the function g of x everywhere. Otherwise, you won't be able to compute this error function at every x, and you won't be able to compute this integral. In practice, we are not going to have g of x. If we had g of x, why bother learning a network to compute the function? You already have the function. So we are faced with a situation where we must learn a network to model a function which is not fully specified. So typically, here is what we will have. We will have samples from g of x, basically input-output pairs for a bunch of inputs x, such that for each x, we know the value of g of x. So rather than having this entire mesh, we are simply going to have for a bunch of x's, we are going to have the function value g of x, which I'm representing as d in this picture. And getting such samples is easy. This is just the process of gathering training data. For example, if you're training a network to classify images, then getting such samples is the same as collecting images and their class labels. If you're transcribing speech, then these samples are going to be speech recordings and their corresponding transcriptions. So collecting such samples from the desired function g of x is easy. And now we are going to try to learn this entire function, but only from this collection of training samples. And so the actual situation we have is something like this. In theory, if you had this entire function g of x, then you could compute this error area given by the shaded area and estimate w to minimize the area. In practice, you're going to have the g of x only at a small set of training points. At those training points, you can compute the network. And there will be a difference between the desired output of the network and the value computed by the network. This is the error. And if you average this error over all of your training samples, this is what we call an empirical error. This empirical error is going to change with W, and we are going to try to estimate the network parameters such that this empirical error is minimized. Again, this empirical error is just our approximation to the shaded area because we don't really know the function g of x. And so we have collected a bunch of samples from g of x, and we are minimizing the average error over these samples with the hope that if you do so, then the network that you learn is going to correctly compute the function g of x elsewhere as well. And so here is our actual objective. We aim to find the network parameters that fit the training points W. Give me a second. So we are trying to find the network parameters that fit the training points exactly. So give me a second. Okay, so I'm sorry, there's a phone ringing here. Okay, so here's the situation. We want to find the network parameters such that the output of the network computes the desired output, which is the value of g of x at those inputs exactly. And hopefully, if we can do this, then the network is also computing the rest of the function correctly in the other locations x. So here's the story so far. Learning a neural network is the same as determining the parameters of the network required for it to model a desired function. For this, the network must have the sufficient capacity to model the function. Ideally, we would like to optimize the network to represent the desired function everywhere. However, this requires knowledge of the function everywhere. Instead, we draw input-output training instances from the function and estimate network parameters to fit the input-output relation at these instances. And we hope it fits the function elsewhere as well. So then to answer the questions that have just popped up, let me start. Can the optimal network architecture be learned? Learning the network architecture is a completely very challenging and a bigger problem than what we're speaking of right now. We are assuming right now that whatever architecture we have for the network is capable of representing the function that we are trying to learn. Now, if the data point you have is an outlier, we are assuming that you're taking samples from g of x. So there's no such thing as an outlier. You're taking samples from g of x, right? And any other questions? So should the training data be too large to model a 3D diagram like we discussed here? We'll get into the business of the insufficiency of training data in a few lectures from now. Let me continue. We have our first goal. Let me Okay, 5 seconds, guys. Let me end the poll. All right, for the first question, what is the answer? Anybody? False. Okay, for the second one, which are the true statements? All true? First three, okay. So let's check what the answer is. First statement is false. The last statement, the parameters can be perfectly learned from just a few training samples, even if the target function is unknown, is obviously false. Because in the places where we don't have training samples, we're kind of hoping it fits, but the odds are it won't. So let's continue, right? Let's begin with a simple task, that of learning a simple classifier. We are going to regressions learn continuous valued functions. We're going to talk about classification. This was one of the earliest problems addressed using MLPs. Specifically, we are going to consider binary classification. This will also generalize to multi-class classification, but I'll discuss in the context of binary classification. Now, consider a very simple problem where the input is one-dimensional and the output is a simple binary classification where the output is either 0 or 1. So for all of your training samples, you're going to have a corresponding output value which is either 0 or 1. In this case, what is the error we are computing? The error we are going to compute is going to be the number of mismatches. So how many times the desired output did not actually equal the actual output of the network. This is the empirical error. And we're going to try to learn the classifier to minimize this count of misclassifications. Now, let's see how we can do this for a very simple classifier, the simplest possible classifier, which is a single perceptron. Remember, the original MLP, as proposed by Rosenblatt, was a network of threshold units. And so we can talk about how we can train a network of threshold units from just input-output pairs. Again, each unit uses a threshold activation applied to this affine value. And the simplest case of an MLP is a single perceptron. So a single perceptron simply has this kind of response. There's a linear boundary, and the output of the perceptron is 1 to one side of the boundary and 0 to the other side. So the perceptron actually represents a Heaviside step function. So Iman, this is again, what are we doing over here? We don't really have the area, do we? For the area, don't you need g of x everywhere? What, Iman, answer?
Yes.
So do we have the function g of x?
No, but aren't we using the training points to approximate it?
So what are we actually computing then?
Like an approximation of g of x.
No, you're trying to minimize the error on the training points. Basically, what we are doing is this. You're only given these guys, the training points here, correct?
Mm-hmm.
And you're trying to estimate the model parameters so that the network passes through these points. The network function passes through these points.
Okay.
Right?
Yeah.
Which means you're trying to minimize the average length of these red lines because that's all you have.
Yep, I see. Makes sense. Thank you.
Right. And so in our binary classification problem, what would the equivalent of that be? That's counting the number of times the actual output of the network was different from the desired output of the network, right? And so this is what we're going to try to minimize. Now, let's consider a single perceptron, which is just only computes a Heaviside step function, except that we are going to try to compute this perceptron's parameters, namely the weights and bias, from only some training samples. You don't actually have the function. All you have are these red and blue dots. And you're going to try to estimate the step function from these red and blue dots. So from given these input-output pairs, basically these dots, where the red dots belong to class 1 and the blue dots belong to class 0, we want to learn the weights and the bias of the perceptron, and in effect, this classification boundary. Basically, you're trying to learn this entire step function, but you're trying to learn this from only the training dots. So the problem is that of learning all of these weights, which I can represent as a vector W, given several training instances where each training instance consists of a vector of features and a class label Y. Is this making sense to you guys? Yes or no? Okay. Please do respond, right? Otherwise I will slow down. So I'm going to, now one of the issues with this is that we have this bias term, and when you have a bias term, Z is affine, right? So dealing with affine things is a bit of a pain. So the way I'm going to do it is, instead of having a bias, I'm going to add this n+1th component whose value is 1. And the weight of the corresponding component effectively becomes bias. So now, in the standard setting, your perceptron has this rule. If the weighted sum of the inputs plus the bias is positive, the output is 1. It's 0 otherwise. Now, in this modified representation, the perceptron fires, the output is 1 if the weighted sum of all inputs is positive and 0 otherwise. So the perceptron fires if a linear function of the inputs is positive and 0 otherwise. And the boundary between when the perceptron fires and when it doesn't is where this weighted sum of inputs is exactly equal to 0. That is now a hyperplane through origin. So does that make sense? Okay. And now here's a magical question. How did we suddenly make a hyperplane that did not pass through origin? Go through the origin by adding a dimension. Anyone? So here's what really happened. So let me try to draw this if I can. You had these inputs, and earlier you had a bunch of positive inputs and a bunch of negative class inputs of this kind, and maybe the origin was here, right? So you're speaking of a threshold which is positive. When I add an extra dimension, what happens is that the positive class inputs end up over here, where the Z values are, 1, because the extra dimension value is always 1, right? So the positive class inputs are going to end up in one plane. The negative class inputs are going to end up in a different plane, and you're actually going to be able to draw a variety of I can't see my thing. I'm having, oh gosh, you're going to be able to draw a variety of hyperplanes of this kind, which separate the two just by adding an extra dimension. I'm having trouble drawing, so I'll take this up over Piazza if necessary. But then here's the point. So eventually we end up with the situation where we are trying to find a hyperplane through origin so that all of the positive instances end up on one side of the hyperplane and all of the negative instances end up on the other side of the hyperplane, right? So actually this figure is wrong. What would be doing? Let me explain this better. What we would be doing is, come on. We are moving all of the data into a hyperplane above. They are the positives and they are the negatives. And then I can draw a line of this kind going through origin, which separates the positives and negatives. And this is how, by adding an offset, I can convert something that's affine into a linear function. Anyway, so we now want to find a hyperplane. that perfectly separates the two group of points, okay? I can write this separately. I can write all of the components of x as a single vector. And so I can write x equals x1 through xn, right? All the dimensions. These are the dimensions of x. I can write, similarly, I can write a weight w equals w1 through wn, right? And then if I write it in this manner, then the equation simply becomes W transpose X equals 0. This is the equation for the boundary. Is this making sense, guys? Sorry for the scribbles, but I'm trying to write with my mouse. Okay, so when you write something of this kind, what is the relationship between W and X? What is the relationship between W and X? Orthogonal, correct? The only time the inner product between two vectors is 0 is if these are orthogonal. Basically, W transpose X equals 0 is the equation for all x's that are orthogonal to W. So effectively, if you're saying there's a vector W, and if I take the set of all x's that are at 90 degrees to W, that's what this equation captures, and that's going to be this hyperplane. These are all the x's that are at 90 degrees to W. This is going to hold true in any number of dimensions, right? So again, we don't have the bias term. Remember Jingtao? We just added this extra component over here and now so the whole thing became linear. So Nimish, do you agree that W transpose X equals 0 means that W and X are orthogonal?
Yeah.
Okay. So W is given. So what is this the equation of? It's a set of all x's that are orthogonal to W, right?
We had X, right?
No, I'm saying if I give you an equation, W transpose X equals 0. What is that the equation for? In some space.
This hyperplane, the dotted one.
Yeah, but what kind of dotted plane? It's the set of all x's that are orthogonal to W, right?
Okay.
Make sense?
Yes.
Okay. So we're not speaking to the training points. We're saying, I want to find a hyperplane of this kind that cleanly separates the red and blue dots.
Oh, okay. Yeah, now I understand.
Right.
Thank you.
So Jingtao, it's on the left-hand side, you actually have a summation going from I equals 1 to n plus 1, because n plus 1 captures the bias term, okay? Now, and so that's basically what we're saying. We're saying W transpose X equals 0 is the hyperplane of all x's that are orthogonal to W. Now, let me ask you another question. Suppose I have a positive instance X. So suppose X is on, I have a vector that's on, suppose I have a vector that's on this side of the plane. Then what is W transpose X going to be? Is it going to be positive or negative? Can anybody tell me? So consider this X, right? That is going to be the sum of this vector and this vector, right? Let me call this x1. This vector is x1, which is the vector from origin to this point. And let me call this x2. So x equals x1 plus x2, right? I'm struggling with my mouse because I can't see the pen. I'm not sure how to make that pointer fatter. x1 plus x2. So when I compute W transpose X, W transpose X is going to be 0 for x1. For x2, it's simply going to be the length of this vector times norm W squared, correct? Because x2 is basically some positive talk, is going to be some positive constant times W, because it's in the same direction as W. Is this making sense? Now, on the other hand, if you had a vector which was pointing away from W, then what is W transpose X going to be? Positive or negative? Negative, because over here, it's like saying it's going to be some x1 minus of some distance times W, right? So in general, what we will have is that W transpose X is positive for all the positive dots. W transpose X is going to be negative for all the dots, the instances from the negative class. And basically, which means that if the angle between this weight vector and the data instance is less than 90 degrees, it's going to be considered positive. If it's greater than 90 degrees, it's going to be considered negative. That's a simple classifier. And we want to find a hyperplane that satisfies this, that all of the positive instance classes are on one side and all of the negative instance classes are, the negative class instances are on the other side, right? Now I'm going to ask you another question. If I'm confusing you, please stop me. So let's say I have a data instance over here. This is my X, okay? And let's say this belongs to the positive class. Now, when you're observing X, you can always get some noise which perturbs it. So given this, what is the decision boundary that's going to classify X most cleanly? Is it going to be something of this kind? Or is it going to be something that's at 90 degrees to X? Which one will be the decision boundary that classifies X most cleanly? The second one, right? So what would the weight vector for that be? You're going to get W equals X, right? Or some scaling times X, correct? Everybody with me on this? I'd like to see some thumbs up if this made sense. I'll wait for 10 or 15 thumbs up. Okay, so here, oh, okay, let me ask somebody. Julio, if X belongs to the positive class, which of these two vectors is a better boundary?
Yeah, okay, I get that the second one is better, but I
Okay,
just
so-
didn't get why W is X.
So if the second one is better, in which direction is the weight vector pointing?
I mean,
It's
which vector?
It's going to be pointing directly at X, correct?
Yeah,
Because the
okay.
boundary is, got it?
Yeah,
So
yeah,
which
yeah.
means the weight is going to be some scaling factor times X, right?
Okay.
That makes sense?
Yeah, okay. And
Okay.
where's the scaling factor included in W equal X?
I've not actually written the scaling factor. You can think of X alpha, but W
Okay.
equals X is the, right?
Okay.
In direction wise, the direction of the best direction for W is X, right?
Okay. Yeah.
Okay. Suppose I have an instance from the negative class. So let's say this guy is the negative class. So this is my X. Then once again, which of these two decision boundaries is the better decision boundary? The one that's at 90 degrees to X or the one that's at some other angle? Can someone tell me? So again, let me draw this again. So let's say I have this data point, and if this data point X belongs to class -1, so this is my X, right? This is my X vector. Of these two decision boundaries, which one is the better decision boundary? Anyone? The second one, right? But then, what is the best weight vector in this case? W equals -X, correct? You want the weight vector to point exactly away from X. This makes sense to everybody? I guess so, because many of you are saying this, right? And so this is the angle. So if I ask myself this question, what is the best way of finding this hyperplane? We're going to base it off this very simple principle. It's an iterative algorithm originally proposed by Rosenblatt. It's an online algorithm, which means that it keeps learning as the data comes in. And it initializes W and incrementally updates it each time we encounter an instance that is incorrectly classified. And it's guaranteed to find the correct solution for linearly separable data. Let's see how it works. You initialize the weight vector W. Initializing the weight vector W is the same as initializing your decision boundary. Then you keep checking through your training instances until you find a training instance that is incorrectly classified. If the training instance that is incorrectly classified is the positive class, then you know that the ideal weight vector for that instance is X itself. So you're going to pull W towards X. On the other hand, if the incorrectly classified training instance is from the negative class, then the ideal weight vector for this is -X. And then in that case, you're going to try to pull the weight vector towards -X. Did this logic make sense? Right. Okay, so here's how it looks like, right? I'll skip the figures, the math. Let's say I have these training data. I'm going to start off with some initial W, guess for W, and the corresponding boundary, which is 90 degrees to it. It's going to classify everything on one side as class 1, and everything on the other side as class 0. Clearly, this guy is making mistakes. So I check through all of my training instances, and I find that this negative instance is being misclassified, which is this vector. So I know that the ideal weight vector for this negative instance is this guy. So I add this guy, which is the negation minus of this vector, to my current weight vector. And that gives me the new weight vector and a new decision boundary. Then I check through all of my training instances again. I find this instance is misclassified. It's on the wrong side. This one belongs to the positive class. So the ideal weight vector for this one points directly at that instance. So I'm going to add and pull my weight vector towards that instance by simply adding it to my weight vector. That gives me the new weight vector and the new boundary. And now I have perfect classification. There's nothing more to be done. And so I'm going to find my optimal decision boundary. If the classes are linearly separable, this is guaranteed to converge in a finite number of steps. Did this procedure make sense to you guys?
Professor, what do we mean by linearly separable classes?
Linearly separable, meaning that it's possible for me to draw a hyperplane that separates the two classes.
Right. Okay.
Correct?
Thanks.
And what would you think would happen if my classes were not linearly separable? Meaning it's not possible for me to draw a hyperplane of this kind.
Yeah. I mean, would we need more dimensions to separate the...
This is the data you have. It wouldn't converge. It would keep on going, right? Because you're always going to find a misclassified instance and you're going to keep adjusting your weight vector, right? There is no such thing as a linear classifier, which you can't find it. And so when the classes are not linearly separable, it's not possible to find a separating hyperplane. So the perceptron algorithm will never converge. If you have data of this kind, the perceptron algorithm will never converge, right? So this is clear, right? But so Jiaming, you're just this is an online algorithm. You keep going through your data till you find a misclassified instance, and then you adjust your W. And there's a theoretical guarantee that in a finite number of steps, it will eventually give you a boundary which perfectly separates the classes. the proof. I think we're putting up the proof on the course page as additional reading, right? So this is great. But now that was for a single perceptron. Now suppose I want to learn an MLP for this function, 1 in the yellow region, 0 outside. Except I'm not given the boundaries, I'm only given the samples, right? Now I know that these boundaries can be perfectly represented by this MLP. So I'm already giving you the structure. All I'm saying is find the weights, okay? So can we use the perceptron learning rule to learn the parameters of this network to classify this data perfectly? We know that there is a setting of these weights which will classify these data perfectly, and we find them. Now, for this to work, here's what happens. Every single perceptron is a linear classifier, right? So the lower level perceptrons are all linear classifiers, which means that if you want to learn these perceptrons, for the perceptron to be learned perfectly, we know that the data that it's trying to classify must be linearly separable. But the data that are actually provided are not linearly separable. What do I mean by this? Let's say magically, so these are all the data that are given, and it's from these data that you have to learn this double pentagon decision boundaries, right? So let's say I gave you this entire network for this double pentagon decision boundary, except I forgot to give you the weights for this one guy. If I forgot to give you the weights for this one guy, everything else is known. Is this network, that means this network is not complete. I'm going to have to learn these weights. So can I learn the weights for this network from the training data I have? Can I learn this for this perceptron from the training data I have? Can I learn the weights for this perceptron from these data? Why not? Can I learn it or not? How would I learn it? These are the data I have. I want to learn the weights for this perceptron. Remember the perceptron rule, they are not linearly separable. I cannot learn the weights, correct? But I know that there is a setting for these weights such that if I use those weights, the overall network is going to be perfect. So what would I need to do to figure out what these weights are? Anybody? Here's what I would have to do. I know that there's a setting. What are you going to repeat? Here's what you'll have to do. You're going to have to relabel some training instances in order to learn this line, right? If I could relabel these instances and say these guys are red and these guys are blue, then I could learn this line, correct? Yeah. So that leads us to hole number 2. Let's see. Okay, 10 seconds, guys. Okay, let me stop this. All right. So for the first question, what is the answer? The answer is no, right? A whole bunch of you answered yes. Now, For those of you who answered yes, let's go back and look at the figure again. From data of this kind, can you learn this boundary? Clearly no, right? The data are not linearly separable. You cannot learn this boundary. So whereas the perceptron learning rule requires linearly separable classes to learn the model that fits the data perfectly. But here the data are not linearly separable, which means that we have to relabel the data to make them linearly separable for the correct decision boundary. And so going back, I know that it is possible for me to learn a perceptron here that classifies the data perfectly. All the other parameters are given. But these are the data I am given. So I know that in order to learn this perceptron, I have to relabel some of the data. How am I going to do this? Do I know which data instances to relabel a priori? No. So then how would I do it? Randomly try by cheating? Any better guesses? By cheating, yes. Any better guesses? Try to find a boundary that minimizes points. How are you going to search for them, right? So it turns out that you need to relabel the data, and this is not given, which means that we have to figure out the labels for this training unit, how to relabel it. And you don't know anything about this boundary. All you're able to verify is the output out here, correct? And you got to make sure that the overall classification is perfect. You know, it's possible. So it turns out that the only way you can do it is to try every possible way of relabeling the data. Try them all till you find a relabeling that gives you perfect classification. Does that make sense? Yes or no? Yes, but shocking. That is true. Correct? It turns out that's the only way of doing it. And so even for a single boundary, you have to try out every possible way of relabeling the dots such that we can learn a line that keeps all the red dots on one side. And if I didn't give you the rest of the network, and if I had to learn the entire network, you're going to find out, you're going to have to figure out, evaluate every possible way of relabeling the data for every one of your perceptrons and explore this entire set till you find a combination that gives you perfect classification on the output. And as Joshman says, you can't. These are high dimensional data, right? You cannot visualize the data. And so this is an exponential search over inputs. This is not going to be feasible, right? And if you get even one of these boundaries wrong, your classification is going to be broken. So we must know the desired output of the neuron for every training instance in order to learn the neuron. And the output should be such that every neuron individually has a linearly separable task, and the linear separators must combine to form the decision boundary. And searching for it in this manner is going to be an exponential problem, exponential in the number of training instances, and it's exponential in time complexity. So clearly, this is not a feasible solution. This is not the way to go about things, right? So training this network using the perceptron rule is a combinatorial optimization problem because we don't know the outputs of the individual intermediate neurons. So during training, we must determine the correct output for each neuron for every training instance. And this is exponential time complexity, which means that perceptron learning rules cannot be directly used to learn an NLP. It has exponential complexity of assigning intermediate labels, and it's even worse when the classes are not linearly separable. So can we come up with something else? Can we use greedy algorithms? It turns out that there were various proposals by Bernie Widrow and such like, Adeline and Madeline. They're on the slides. Please look them up. Brilliant algorithms. I'm going to skip in the class, but they will turn up in the quiz. but they didn't quite cut it. So here's the story so far. Learning a network is the same as learning the weights and biases to compute a target function. In practice, we learn the networks by fitting them to match the input-output relationship of training instances drawn from the function. A linear decision boundary can be learned by a single perceptron in linear time, where the classes are linearly separable, but nonlinear decision boundaries require networks of perceptrons. And training an MLP with threshold function activation perceptrons requires knowledge of the input-output relationship for every training instance for every perceptron in the network. These must be determined as part of training, and this is an NP complexity combinatorial optimization problem that's not feasible. So the realization that training an entire MLP was a combinatorial optimization problem stalled development of neural networks for well over a decade. So, Tanmay, I'll keep track, don't worry about it, okay? Now, why do we have this problem? To see why we have this problem, the issue is this. The binary class of error metric that we used is not useful. Now over here, if the green line shows the ideal classification function, the x1 and x2 are class 0, x3, x4, x5 are class 1, then let's say my current setting of weights gives me this classifier. If I find that this classifier is misclassifying 2 instances. Now, if I change the weights a little bit, this classifier is going to move right or left a little bit. But if this moves a little bit to the right or a little bit to the left, will it change the overall classification error? No, right? You have to move it a whole lot before it crosses one of these points. So you'd have to move it if you want to figure out whether you want to move this boundary right or left, you'd have to move it past this point to know that you're going in the wrong direction. You would have to move it all the way past this point to know that you're going in the right direction. Small perturbations are not going to tell you anything. And so you have this problem, right? Same thing. If I have a high dimensional problem, I'm showing something in 2 dimensions. This blue boundary is not classifying this red dot. I can swing it around all the way from here to here, and the classification output is not going to change, error is not going to change, which means that I will never know for a very long time whether I'm moving in the correct direction or not. There's no indication of which direction to change the weights in to reduce the error. And this gets compounded as the functions become more complex. The individual neurons' weights can change a whole lot in problems like these without changing the overall error. Meaning the simple MLP is a flat non-differential function, meaning that the function has a 0 derivative nearly everywhere and no derivatives at the boundaries, meaning if I move at this point, moving the network left or right doesn't change the error at all. The error is 0. Over here, just moving the point just past the boundary just past this point makes the error go from 1 to 0. So it's an infinite derivative. Either way, those derivatives are useless. And so we want to change our way of thinking. We want to change our way of computing the mismatch such that modifying the classifier slightly lets us know if we are going in the right way or not. Now we have 2 issues. One is the activation function of the classifier. So far we've assumed it's a threshold activation. The other is the manner in which we evaluate the mismatch between the classifier output and the target output. For a classifier, what we did was to count the number of misclassifications in what we just saw. We are going to change that. We're going to change the activation, and our mismatch function will now not actually count the errors, but a proxy for the errors. So instead of having a threshold activation over here, we are going to make this neuron differentiable with an activation function that has non-zero derivatives in most places, like a sigmoid or one of these activations. And so here, small changes in weight can result in non-negligible changes in the output. This, of course, requires us to estimate the parameters using gradient descent, but we'll see that again. Now, to illustrate what I mean, consider this problem again. If I have a binary classification problem on a single input, these are all class 0, the blue dots. The red dots are class 1. In my standard classifier, if it's a linear classifier is just a threshold. A threshold at T1 misclassifies one instance. If I move the threshold backward from T1 to T2, it still misclassifies one instance. So in this case, did I get any indication whether moving T1 to T2 is improving the function or not? Do I know whether I should continue moving it backwards or not? I don't, right? So here's what I'm going to do. I'm going to change my activation from a threshold to something like a sigmoid. The classification is going to be, output is going to be 1 if the sigmoid value is greater than 0.5 and 0 if the sigmoid value is less than 0.5. So, in terms of classification, it's doing the same job. I've changed the activation, but then I'm also going to change the manner in which I compute the error. Instead of simply counting the number of errors, I'm going to count the total distance from the desired output to this curve. So I'm going to count the total length of these dotted lines. And when I do that, you will see that as I move from T1 to T2, this total length actually decreases, which tells me that continuing to move in that direction is going to continue to decrease that length. And so that's a good thing to do. So the thing is this really counting error? Or is it counting a proxy for error? It's counting a proxy. Will minimizing this minimize error? Okay, let me give you an example. Let's say I have like 1 billion points out here. What will happen? This line never quite becomes 0, 1, correct? So the cumulative error from these 1 billion points is going to be so large that if I have only 10 points out here, misclassifying these 10 points is going to be fully compensated for what I gain by reducing the error even further for these billion points. So these billion points are going to keep pushing this curve all the way out back. Yes or no? Tanmay, did that answer your question? Right, and so this is not really the error that you're computing. It's a proxy for the error. It's making some assumptions about the balance in the data and such like. But it gives you a handle. It gives you something that you can compute and you can try to reduce, and in reducing it, you expect the overall error to reduce. That makes sense? Yes, no? Okay, give me a bunch of yeses, guys, before I continue. Or thumbs up or whatever. Questions so far? It's a very cool idea, right? And so I'll try to put up the paper. And so here's my third poll. So Jinta, the idea was, I forget the name of the guy from MIT. It was a PhD thesis from MIT from 1972 or 74, but it was really popularized by Jeff Hinton in the late 80s. So Hinton became famous for this work, backpropagation, right, which is based on this idea. I'm trying to recall the name. Well, 5 seconds, guys. So Bilal, I'm just using a sigmoid as a matter of illustration. But your classification, in your classification networks, your final output layer is always a sigmoid because it computes something that looks like probabilities, which is why I'm using the sigmoid. And in the good old days, in fact, neural networks almost entirely use sigmoids. We found these other activations to be better. And Bilal, on the topic, why do we use ReLUs rather than sigmoids inside the network? Because they continue to tell you the different distance from the boundary, quite far away from the boundary, whereas a sigmoid doesn't. Anyway, which of these statements are true in the first question? The first two. And the second one? Okay, let's see. Right? So increasing or decreasing the threshold will not change the overall classification error. And we cannot know if a change moves it in the correct direction. That is true, right? And there is no derivative. The derivative is always 0 or infinity. Whereas for the second case, all three statements are true. Shifting it will not change the overall classification error still, because the the value at which the function becomes 0.5 has to move past the point. Nonetheless, it's going to change the total distance of the function, of the value of the function from the target value. And so this gives us a derivative, which tells us whether we are moving in the correct direction or not. So it's a very beautiful idea, right? And so here are the two ideas we've got. We've got a continuously varying activation, which is differentiable, and a continuously varying error function, which is also differentiable. And by differentiable, we mean that we are able to compute how much the output changes, how much the value of the function changes for a small change in the input. And this is key, right? So the continuously varying activation, this is differentiable, which means that instead of using a threshold activation, we are going to use other kinds of activations. I've seen a sigmoid, I've shown you a sigmoid, but anything that is that actually varies continuously with the input works. And you want the function to be differentiable, have non-zero derivatives almost everywhere. And if it does have the occasional corner of this kind, you must have something called a subderivative, meaning it must be possible for me to draw a plane or a line that lies entirely below the function at this discontinuity. We'll see that more on that later. That's for the activation. And specifically, if you're looking at the sigmoid activation, this has a very nice interpretation. It can be interpreted as the posterior probability of class 1 given the input. How this is so is explained in the slides. I'll skip that because we will be out of time if I spend time on that. So we'll return to the fact that perceptrons with sigmoid activations actually model class probabilities in a later lecture. For now, I'm moving on. So here is what we've got. Our perceptrons are now of this kind, where you first compute an affine function of the inputs and put this affine value z through an activation that is differentiable. So what this means is that if the activation as function is differentiable, then I can tell you, what does it mean for something to be differentiable? That's right, Paul Verbos. Thank you, Katrina. So what does it mean for a function to be differentiable? Anybody? What does it mean? Continuous? Anybody else? It has a slope, right? Basically, what it means for a function to be differentiable is that you will be able to compute how much the output changes for a small change in the input. Meaning, if I change the xz by a small value delta z, I will be able to tell you whether y, how much the value y changes in response. So the activation function is differentiable. But then this affine function is also differentiable. If I change this parameter w a tiny bit, I can compute how much z will change. And if I change the parameters, the z value a tiny bit because of the differentiability of this activation, I can tell you how much y will change. So this overall perceptron is differentiable with respect to the w's. Similarly, it's also differentiable with respect to the x's. Meaning I can tell you how much a small perturbation of the x is going to change the y. Does that make sense? Right. And this is beautiful. Why is this beautiful? Because when I look at a large network now, this means that since every perceptron is so differentiable, I can tell you how much a small perturbation of this W will change the output of the perceptron. Now, that in continuing on, I can also tell you how much a small perturbation of the output of this perceptron is going to change the output of this perceptron. I can also, and so also how much a small perturbation of this perceptron is going to change the output of this perceptron, which means I can tell you how much a small change of this guy is going to change the outputs of these two perceptrons. But then this guy is also differentiable. So I can tell you how much small perturbations of its inputs can change the output. So putting it all together, I can now tell you how much a small change of W is going to change Y. Whether increasing W by a tiny bit will increase Y or decrease Y. That their ability to compute that now becomes feasible, which means that the entire network is now differentiable with respect to every parameter of the network. Did that make sense? Yes, no? So I'd like to see some thumbs up. Having 5 people respond is not. What about the rest of you folks? That makes sense. And that's beautiful, right? Because now it means that the overall function is differentiable with respect to every parameter of the network. We can compute how small changes in the parameters are going to change the output. Exactly how we compute it is done during the chain rule. We'll see that in the next class. And so for threshold activations, we can't do this because small changes in the parameters of the input don't change the output at all unless you're at some critical point where the output is going to change by a massive amount. But for continuous valued differentiable activations, we have this characteristic that you can compute how changing each input changes the output. Now add to this the fact that we want the error function to also be differentiable, meaning you want to know, you want the error function that you compute, which is the sum of these lengths, to be such that you know how much it changes if the output of the network changes a little bit. And so put all of that together. Now, this is the error function, right? Which computes the difference between the actual output of the network and the desired output of the network. If that is also differentiable with respect to the output of the network, then I have the output of the network with respect to being differentiable with respect to the parameters of the network. So I can tell you how much a small change of the parameter will change the output. I can tell you how much a small change of the output is going to change the error. And so thereby I can tell you how much whether a small change of the parameter is going to increase the error or decrease the error. That makes sense? Yes, sir. Right? And so that's what we're going to use to train the network. Beautiful, isn't it? I mean, just the whole concept just falls into place. And so, but for this, we need the error function to be differentiable. And so we're going to define a divergence function for the error. You know, counting errors, are the two outputs the same? Didn't quite cut it. So we needed some way of measuring the gap between the desired output and the actual output. And we're going to do this using a divergence function. And the divergence function quantifies the gap between the desired output and the true output. And What does it mean to be output differentiable? It's differentiable with respect to the output of the function, which means that we are saying that the error function is differentiable with respect to y. That answer you, Mingro? Right. And y is differentiable with respect to w. So the error is differentiable with respect to w. And so now we're going to define a divergence function as our error. You can define your error, right? And we are going to have these requirements. This divergence function will be 0 only when the output of the network is exactly the same as the desired output of the network. If the output of the network is not the same as the desired output of the network, then it will always be positive, regardless of whether the desired output is above the actual output or below it. If the two are not the same, the divergence is going to be positive. And there's no notion of greater than or less than, right? Because the divergence is the measure. The third property that we will require is that it's going to be differentiable with respect to this argument, which is the output of the network. If we have such a divergence function, this is going to quantify the gap between the actual desired output of the network and the actual output of the network. Again, for classification, this is not the classification error, just a proxy to it. And now once you have a desired output and define a divergence, we can compute the shaded area as the integral of this divergence function over the entire input. But then I'm going to add one little bit, right? So suppose I find that the input always lies in this range, and in real life, you're never going to see inputs outside this range. Then would you want to expend any effort minimizing the error here and here? Would you want to do that? It's not worth it, right? So what we are going to do is to modify our error function a little bit. We're going to say that at every point, the error that we want to minimize is going to be weighted by the probability that the input can take that particular value, which automatically is going to say that things that are impossible contribute nothing. Things that are very rare are going to contribute a little bit. Things that are very frequent are going to contribute a lot. And so the actual term that we are going to try to minimize is this integral of the divergence between the desired and actual outputs of the network multiplied by the probability of the input over the entire input space, which is the expectation of the divergence between the desired and actual outputs of the network. This is what we'll minimize with respect to W hat. No, hang on, Aish. But then we don't have G of X, right? So we want to sample G of X. But then when we sample it, here is the thing. If you sample data in a natural way, you're naturally going to get more samples out here and very few samples out here, right? Yes or no, Aish? Yes. And so if you simply collect samples properly, then the samples of X are naturally going to be drawn from P of X. And so instead of trying to compute the expected value of the divergence, if I simply compute the average divergence over all of my training samples, this is going to be our approximation for the expected value of the divergence. And this is what we're going to try to minimize. So here is the overall problem setting that we have. It's what we will call empirical risk minimization. You're given a set of training data, input-output pairs, input and desired output pairs. We define our own way of quantifying the error between the actual and desired outputs of the network. We will compute the average divergence over the entire training data. And since the training data, the X's are given, the only way to change this guy is by changing the parameters W. So this term, which we'll call our loss, is a function of the network parameters. And we are going to try to estimate our network parameters to minimize this loss. So this term is our empirical risk. It's called empirical risk because it's the loss, it's the error that you make over the drawn samples, things that you have observed, what is empirical. And you're going to try to minimize it. So again, observe that this term here is a measure of error but using standard terminology, we'll call it a loss. And this empirical risk is only an empirical approximation to the true risk, which is the expected divergence, which is what we really want to minimize. In other words, we really want to minimize the shaded area, but we're going to be minimizing the average error over all our training samples. Right, and so here's the overall problem statement. We're given a collection of training samples. We define our loss function as the average error over all the training samples, and we try to minimize this with respect to network parameters. And this is a problem of function minimization. I have a function of network parameters. I'm going to try to minimize it with respect to its argument. It's an instance of optimization. So that's what we are, right? So ending our lecture, we learn networks by fitting them to training instances drawn from the target distribution. Learning networks of threshold activation perceptrons requires solving a hard combinatorial optimization problem, so we won't do it. Instead, we use continuous activation functions with non-zero derivatives that enable us to estimate network parameters. It makes the output of the network differentiable with respect to every network parameter. And we define a differentiable divergence between the output of the network and the desired output, and a total error, which is the averaged divergence over all training instances. This we'll call our loss. And we optimize the network parameters to minimize this error. This is empirical risk minimization. So it's an instance of function minimization. We'll cover that, the ERM itself, in the next class. So thank you. I'm just a minute over, but I can take any questions. Siddharth, what we call our loss is our proxy term, the average divergence. And the divergence is measuring the error between the desired and actual outputs of the network, the length of those dotted lines. Did that